If we're going to learn how to balance a particular kind of reaction called redox reactions, where certain atoms lose electrons and hence are oxidized, and other atoms gain those electrons and hence are reduced, we're going to have to learn how to quickly calculate what are called oxidation numbers. And in every reaction, every atom has a certain oxidation number that represents to what extent they've been oxidized. Positive oxidation numbers would mean they have been oxidized a certain number of times, and negative oxidation numbers means they've experienced the opposite of oxidation, namely they've been reduced, they've gained electrons. Now, if we look at these example atoms, the first rule of the 5 that lets you calculate oxidation numbers is the easiest, and that is for elements, neutral elements in a reaction. Clearly, since they have yet to combine with other elements and therefore can't get oxidized or reduced yet, they have oxidation numbers of 0. They have yet to have an extent of oxidation. And that would mean the chlorine in this reaction and the aluminum in this reaction both appear as elements. They have yet to be oxidized or reduced. They have 0 as oxidation numbers. That would also be the case of the oxygen in pentane being burned. Even in a very complex redox reaction involving a net ionic equation, the iron appears as an element and therefore it has yet to be oxidized. And even in this other redox reaction, net ionic equation, oxygen appears and it's an element, so it has yet to be oxidized. So all elements in a reaction that have yet to react and are neutral have oxidation numbers of 0. Rule 2 may be even easier because it involves monatomic ions, single atoms that have gained or lost electrons and therefore have a charge as a consequence of being oxidized or reduced. And in that case, the oxidation number of the atom is the same as its ionic charge. For instance, a sulfide ion, which is S-2, has a -2 charge because it's gained 2 electrons. It's been reduced twice. And so, of course, its oxidation number would also be -2. Now, there are some monatomic ions in this compound called aluminum chloride. These are chloride ions, and since chloride anions have a -1 charge, these 3 atoms all have oxidation numbers of -1. And the aluminum cation, which always has a charge of +3, well, that makes this aluminum atom in the products a +3 oxidation number. Now, there are no ions in the second equation because it is a molecular reaction, but we have a number of monatomic ions in the third reaction. We have 14 protons, and since protons have +1 charges, they, of course, have an oxidation number of +1. These 2 iron 3 cations are +3. The 2 chromium cations are also +3 in their oxidation numbers. And in the final equation, I see manganese cations that have to be +2 for oxidation numbers, and protons that are again +1 for oxidation numbers. So all monatomic cations and anions, once again, have oxidation numbers equal to the monatomic ion's charge. Now, the third rule involves oxygen in compounds, that is, when it's combined with other atoms. Now, since oxygen is the second most electronegative atom after fluorine, in other words, it wants electrons more than any other atom except for fluorine, which is a rare atom and hardly seen in most instances. Oxygen is also divalent and tends to share 2 electrons with other atoms, form 2 covalent bonds, and for this reason, in compounds it's almost always -2 for an oxidation number because it's so electronegative. When it shares twice with other atoms, it really draws the other atom's electrons towards it, and it's as if it's stealing them and is acquiring a -2 charge, which it isn't. But it's said to have an oxidation number of -2. It always tends to get reduced by other atoms. Now, that would be the case, not at all in the first equation, But in the second equation, we see oxygen in two compounds, carbon dioxide and water. And in both cases, both of these oxygens in carbon dioxide would be -2 for oxidation numbers, and the oxygen in water would also have a -2 oxidation number, as would all 7 of the oxygens in the dichromate ion, and the 7 oxygens in 7 water molecules, as well as the 4 oxygens in permanganate, and the oxygen in water. They would all be -2. However, there are some exceptions. The most obvious is Rule 1 overrides, and if you see oxygen in its elemental form unreacted, it's still 0. But most important of all, if you see a superoxide or a peroxide ion, you have to be careful. And in this particular reaction, we have hydrogen peroxide. These two oxygens combined have a -2 charge, and therefore oxygens in peroxide are said to have a -1 oxidation number. Now in the superoxide ion, 2 oxygens are sharing 1 additional electron, and even though you can't have half an electron on an atom, the 2 oxygens exchange that 1 electron, and they're each said to have a -1/2 oxidation number. Fortunately, these are very rare exceptions. So, oxygen in almost all compounds is -2. So oxygen in combined form with other elements is almost always -2, with the rare exception of peroxide ions and superoxide ions. And of course, if it's elemental oxygen, it's still going to have an oxidation number of 0. Now, hydrogen in compounds, combined form, almost always has an oxidation number, excuse the typo, that shouldn't be have, that should be has, an oxidation number of +1. And this is because hydrogen is one of the least electronegative atoms of almost all elements. Exception would be the larger group 1 elements, the lithium, sodium, potassium. Those are a little less electronegative still than hydrogen, but because it doesn't have much of an attraction for electrons, when it combines with other atoms, its electron gets pulled away from it. It gets oxidized, and it only has 1 electron, so it's usually +1 in combined form. That would be the case of all the hydrogens here in the pentane. They'd all have an oxidation number of +1. So with the 2 hydrogens in water, we already know the protons must be +1. But again, hydrogens in water, hydrogens in peroxide, and hydrogens in water, all +1. And yes, now we see all hydrogens in compounds are +1. And you may ask, what are the exceptions for hydrogen? Well, it's if it appears as a hydride ion, and you would know it when you saw it, because a compound such as sodium hydride is clearly an ionic compound with the metal cation first. And if sodium's +1, then you can deduce that hydrogen has in fact been reduced and gained an electron, and therefore it's -1 as its oxidation number. And of course, hydrogen will only form hydride in the presence of group 1 metals, so it will be easy to spot the exception when hydrogen is not +2 in a compound. And if you're thinking, well, that still leaves a lot of atoms with unknown oxidation numbers, well, you're right, but the other numbers can be deduced by the 5th rule, which is really a little mathematical exercise, namely the sum of all the oxidation numbers of all the atoms in a particular compound or species must equal the charge on the species. Now, what does that mean? Well, it makes sense here. If this is 0, the charge is 0, this is 0, the charge is 0, and a +3 and 3 -1s add up to the total ionic charge on aluminum chloride of 0. But it can be a useful tool when we're calculating other oxidation numbers. For instance, what if we want to know the oxidation number of the carbon in carbon dioxide? Well, we already know the 2 oxygens are each -2, that's -4 total, and therefore the one carbon has to be +4 for the whole molecule to be neutral. So yes, in carbon dioxide, carbon's oxidation number is 4. It's also useful in something like dichromate, because when you consider the dichromate ion, there's 7 -2 oxidation number oxygens. That's -14 total. And the only way the ion as a whole could be -2 is if the 2 chromium oxidation numbers added up to +12, because +12 and -14 would be -2. That means each of the 2 chromiums must be +6 for oxidation numbers. Down here, in a permanganate ion, if we know that all 4 oxygens have a -2 oxidation state, that's -8 total. And for all of the oxidation numbers to add up to -1, the one lone manganese atom has to be +7. +7 minus 8 would be -1. So it's very helpful in determining oxidation numbers of unknown atoms. And if you're wondering about the pentane and the carbon atoms in pentane, well, +12 for the 12 hydrogens, and the carbons must add up to -12 if the molecule is neutral. And if you divide -12 by 5, you get a -2.4 oxidation number for each carbon. Now, that's not possible. An atom can't gain 4/10 of an electron. However, if you looked at the structure of pentane, you would notice that 3 of the carbons bond to 2 hydrogens, and they actually have -2 oxidation numbers, and 2 of the carbons bond to 3 hydrogens, and those 2 carbons actually have a -3 oxidation number. So the average amongst all 5 of the carbon atoms is -2.4. So almost all other oxidation numbers can be calculated by using the first 4 rules for known oxidation numbers and deducing the other oxidation numbers by simple mathematics. However, there are some unusual exceptions to which all the rules don't apply. So I've sort of developed a 6th rule that I like to call my own rule, that if you have things like hydrogen cyanide or hydrocyanic acid, depending on whether or not it's in water, and you do know the oxidation number of hydrogens +1, but you don't know carbon or nitrogen, and you don't know either of the elements in sulfur hexafluoride or radon tetrafluoride, how do you figure out what the numbers are? And it's pretty easy, because atoms are essentially listed in order of increasing electronegativity. And as such, you can determine that typically the last atom in the formula is the most electronegative, and therefore would have the same oxidation number as if it were a monatomic ion of that atom. Now, fluorine is in group 7, and when it gets reduced, it usually gains 1 electron and forms a -1 anion. So in radon tetrafluoride, yes, the fluorines are each -1, and since the molecule is neutral, the radon must be +4 using rule 5. They have to add up to 0. In the molecule sulfur hexafluoride, same deal. The fluorines are each -1, and since there are 6 of them, that's -6, and the lone sulfur atom would have to have an oxidation number of +6. And lastly, in something like hydrogen cyanide, we know the hydrogen is +1, and if we treat the nitrogen like an anion of nitrogen, being a group 5 atom, the nitrogen would of course be -3. And so +1, -3 is a total of -2, so our carbon is going to have to be +2 in this example. So this is kind of an important little rule to know. If you ever encounter more than 2 atoms for which you're uncertain of the oxidation number, always treat the last atom as the most electronegative and the most likely to have the same oxidation number as its monatomic ion. I hope this helps with understanding oxidation numbers.